Now in the fourth unit of the course, we're going to move on and start talking about congruence modulo n. In this video, we're going to introduce the definitions and make a few initial observations. So what is the definition? If a and b are two integers and n is a positive integer, where n is a factor of the difference a minus b, then we will say a is equivalent to b modulo n, written as a equivalent to b modulo n. If n is not a factor of the difference, we can write a is not equivalent to b modulo n. I do want to point out that n, which we'll refer to as the base, must be a positive integer. A and b, however, could be negative, could be positive, it's not specified. Also, there's a difference between this triple line equivalence symbol and the double line equality symbol. Do try to keep them straight. So for example, 3 equivalent to 5 mod 2 is a true statement, since 2 is a factor of the difference, 3 minus 5. 3 minus 5 is negative 2, and 2 is a factor of negative 2. So therefore, 3 is equivalent to 5 modulo 2. 6, however, is not equivalent to 10 modulo 5, as 5 is not a factor of the difference 6 minus 10. Now, some of you may have seen notation that might look like what I have here, 5 mod 2 equals 1. This is different notation with slightly different meaning. Okay, we'll address the difference between the two notations and what this notation here means, but in our notation we use an equivalence and not an equal sign. Also, in the a mod n equals b notation, it's actually very much required that b, the thing on the other side there, must be in between 0 and n. We do not have any such restriction on b. A and b can both be arbitrary integers in our notation. Well, if we're going to be using the equivalence sign, hopefully this is an equivalence relation. So let's show that now. If n is a fixed positive integer, then a equivalent to b modulo n, as defined previously, is in fact an equivalence relation. So we need to show this is reflexive, symmetric, and transitive. For reflexivity, we want to show that any integer a is related to itself. In other words, that a is equivalent to a modulo n. Since n is always a factor of 0 regardless of n, and a minus a is certainly 0, n is a factor of a minus a, therefore, a is equivalent to a modulo n, a is equivalent to itself. For symmetry, suppose that a is equivalent to b modulo n. What we need to show is that b is equivalent to a. But if a is equivalent to b modulo n, by definition, n must be a factor of the difference a minus b. Therefore, n is a factor of negative 1 times that. Remember, factoring does not care about multiplication by negative 1. So if n is a factor of a minus b, it must be a factor of negative a minus b, which once you distribute is b minus a. But if n is a factor of b minus a, then by definition, b is equivalent to a modulo n. So we've established symmetry. When a is equivalent to b modulo n, b must be equivalent to a modulo n. Now let's address transitivity. Suppose a, b, and c are integers. A is equivalent to b modulo n, and b is equivalent to c modulo n. So by definition, since a is equivalent to b, n must be a factor of a minus b. And since b is equivalent to c, n must be a factor of b minus c. But when one number is a factor of two different numbers, and for this we are considering this entire parenthetical term one number, a minus b, and this is a single number, b minus c. If n is a factor of both of those numbers, it's also a factor of the sum, in which case the b's cancel out and n must be a factor of a minus c. Therefore, by definition, a is equivalent to c modulo n, our desired conclusion. So this relation is reflexive. Any integer is equivalent to itself, modulo n. It's symmetric. If a is equivalent to b, then b must be equivalent to a. And it's transitive. If a is equivalent to b and b is equivalent to c, then a must be equivalent to c. So this is in fact an equivalence relation. So what is the relationship between our notation and what you may have seen somewhere else, a mod n equals b? So here is how the two notations are related. Here is our notation, a is equivalent to b modulo n, if and only if the remainder, when a is divided by n, is the same number, notice this is now an equal sign, as the remainder when b is divided by n. Now this alternate notation that you may have seen somewhere else, a mod n, exactly means the remainder when a is divided by n. So this is completely redundant with this notation here. And since we've already been using this to represent the remainder in the division algorithm, we're going to keep using that. But here's the relationship between them. A is equivalent to b modulo n if and only if they have the same remainder when divided by n. Well, first, let's suppose they have the same remainder. So let's suppose that same remainder is r. So by the division algorithm, I can write a is one multiple of n plus r, and b is a different multiple of n plus r. Possibly the same multiple. I don't really know that k1 and k2 can't be the same number, but they don't have to be. Then if I take the difference, I simply write a minus b and substitute in what we just assumed up here are representations of a and b. Well, then the r's cancel, and what's left has an n that can be factored out of it. Therefore, n is a factor of the difference, and thus a is equivalent to b modulo n. So if they have the same remainder when divided by n, then they are equivalent modulo n. Let's go the other way. Let's assume that they are equivalent modulo n. So n is a factor of a minus b. Let's let r1 and r2 be the two remainders when divided by n. Therefore, I can write a is a multiple of n plus r1, and b is a multiple of n plus r2. So therefore, the difference must be n times some integer plus the difference of the remainders. Now, n, by assumption, is a factor of a minus b. N is definitely a factor of n times k1 minus k2. Therefore, we can factor n out of a minus b minus n times k1 minus k2. If n is a factor of this number, and it's a factor of this number, then it's a factor of the difference, but this minus that is just r1 minus r2. Therefore, n must be a factor of r1 minus r2. But r1 and r2 are both between 0 and n, and they can't be equal to n. So their difference cannot be negative n, and it cannot be positive n, but it must be somewhere in between. But it has to be a multiple of n. We've already determined that n must be a factor of this difference. Well, negative n is n times negative 1, and positive n is n times 1. The only multiple of n strictly in between them would be 0. So since r1 minus r2 can't be as small as negative n or as big as positive n, and it must be a multiple of n, it must be 0, meaning r1 equals r2. Therefore, the remainder, when we try to divide by n, is equal. So this shows that this notation a mod n equals b is entirely redundant with our notation from the division algorithm, and it's a little bit redundant with what we've just established as our notation for a being equivalent to b mod n. Two integers are equivalent mod n exactly when they have the same remainder when divided by n. So let's discuss what we've established in this brief introduction to congruence modulo n. First, a is equivalent to b modulo n if and only if I can write a is equal to n times something, a multiple of n, plus b. Well, this is exactly the definition that n is a factor of the difference, a minus b. When we're proving stuff about modular equivalence and beyond, we're frequently going to jump directly from assuming that a is equivalent to b modulo n to simply stating a is a multiple of n plus b without making that intermediate statement n is a factor of a minus b. So we've just seen here, a is equivalent to b mod n if and only if I can write this. So from now on, we'll just jump right from here to here. Now do be careful about the difference between equivalence and equality. Writing the equal sign means you are saying the two things are exactly the same number. This equivalence sign has a definition behind it, however. So if you were to write 3 is equivalent to 5 mod 2, that would be true. If you wrote 3 is equal to 5 mod 2, that is not true. So why not? Consider how parentheses could possibly be placed in that later statement. If you attempted to put the parentheses around 3 equals 5, this doesn't make any sense. The notation a mod n equals b requires that a be an integer. But 3 equals 5 is not an integer, it's a logical statement. It's in fact a false statement. But whatever, it's a statement, not a number. And I can't say logical statement mod 2, that just doesn't make any sense. But I also can't put parentheses around this bit over here, because 5 mod 2 refers to the remainder when 5 is divided by 2, which is 1. And 3 equals 1 is just not true. So no matter how you attempted to place parentheses in this statement here, it wouldn't make any sense. It would either be totally senseless if you put parentheses here, or it would be false if you put parentheses here. So that is just not a true statement. 3 equivalent to 5 mod 2, however, is a true statement since 2 is a factor of the difference. So do distinguish equivalence modulo n with equality of integers. The equal sign is very, very strong. It means the two things on either side are exactly the same thing. If you don't mean that the two things on either side are exactly the same thing, then don't write the equal sign. Also, we're never going to use from this point forward the notation a mod n. It means exactly the same thing as the remainder when a is divided by n, and we already have notation for that, so we're going to stick with this a % n to specifically mean the remainder from the division algorithm. So anytime we use the term mod, we mean this equivalence relation, not anything else.